Swayam Prabha. Digital India. Educated India.
Yesterday there was a suggestion from one of the students that can we have a summary of what we learned so far, so it will help us with the continuity. So to summarize what we learned in the morning session was that containers are programs that run in an isolated space, and uh, on a single operating system there can be multiple containers, and each container will have visibility limits and resource control limits and a limited view of the global file system namespace. That is, they will see their own root directory and everything that they want. And we have uh, the basic kernel features such as C groups and namespaces, and the very old feature called chroot to make this happen. And we saw that C groups are actually control groups, and there are resource controllers for control groups. And these resource controllers limit how much resources can each program consume, and the namespace limits what the container programs can see or what they cannot see. And chroot limits the visibility of the global namespace. And we saw that containers are nothing but just programs that are packaged in a special way with all their dependencies in a directory and placed in a repository by the developers. And when deploying the containers, that means when it is actually needs to be run on a system, that's when we call it ops. They are pulled from the image repository and they are given to the container runtime, such as Docker or Containerd, which then takes care of reading the image, understanding the limits and everything they need, and set up the environment accordingly for them and starts it off. And the underlying infrastructure, such as C groups and namespaces, can be seen under the proc file system and the sysfs C group file systems, as we saw. So this was the summary of what we learned. So what we're going to look at now is some of the challenges when we saw about limiting the resource consumption and limiting the visibility of the programs. But what are the challenges that some programs face when they are run inside a container? So one of the things that we realize in namespace is that while it gives them full flexibility or the feel of a system, the resources that are given, for example, if a container were to run on is running a web server on port 80, it doesn't actually mean that it has the exclusive access to port 80 on the host system itself. It just means that it has the ownership of port 80 on the container. Inside its limited visible space in its own namespace, it has port 80, but it doesn't really have port 80 on the external host. But this becomes a problem because for all that we do here, the experience for the external program should not change. That means they should not know that whether this program is running on the host or on the container. So we need some kind of a solution to bridge this program to the external world. And that's where the networking challenges originate from. It means this is what we see, that even if the program wants to reach the external network, it must be able to do it as if it is actually on the host system and not in an isolated jail. And an external program must be able to reach it with the same kind of seamlessness. So this is what is the basic challenge of networking, and it is achieved by having a proxy service. That means the container runtime can act as a bridge. That means a given port in a particular container can be bound to the port on the actual host, so that the experience for both the container and an external program remains as if the program running in the container is actually running on the same host itself from a networking point of view. And there was another challenge of we talked about the ephemeral nature of a container, means that it can shut down and restart anytime. So as and when it restarts from one place, one host, and we also saw that because it is completely portable, it can be started on any other node. The connectivity must remain seamless. That means every time a container starts, no matter on which host, all the necessary setups must be done automatically for that particular program. And the container image contains a good amount of information that tells the container runtime what setups it needs. So one of the things that you will see in the Kubernetes world is that services are usually just like on the internet. You identify a service using the name service, but since within the container world itself, the container can move around. Other containers that try to reach it will also have to use the name service to reach there. And there are other technologies that allow service mesh. For example, if you want to pass on message from one container to another on a regular system, if you had two processes, you would probably use some kind of an inter-process communication. But in the container world, you don't know where your the other program that you are trying to connect with may be running. So you need some kind of a networking service to connect them together. This is what we call a service mesh that has also evolved in the last few years to serve this particular need. So how do we open up a container, networking for a container? So in this picture, what you're seeing is this is the same picture that we saw earlier. That means we have the image repository here, and we have the dev tools that push the image. We have the ops tools that pull the image, feed it to the container runtime, which decodes and deconstructs the image into the local storage and instantiates the containers, and all the necessary restriction of uh, namespaces and restrictions on the resources are implemented by C groups and namespaces inside the kernel. So how exactly does the networking work for a container? So networking requirements are specified when the container image is built using the port and network options. This is what I talked about, the two-stage development process. The first part doesn't change, where you take a program in your favorite programming language, you have built it. The second part is converting or packaging that program in a container form factor. When you do that, you specify the resources needed, and one part of it is to say what kind of networking support do you need whenever this container runs. And these requirements are codified and encoded in the container image. And when the image is fed to the container runtime, the container runtime allows the network requirements to be specified when launching the container. And the local ports are mapped to the external ports. Either you can say, I want port 80 on my external on my operating system, or you can just say, well, any port is fine as long as I have a connectivity. Either one of them is possible. And the outside programs, anyone who tries to reach it will rely on the DNS service to connect to a program on the container. Okay, so let's time for a little bit of hands-on again. Now we'll try and see how the networking looks for any particular container that's actively running. So again, we open up our Ubuntu terminal, and in the Ubuntu terminal, I have already started Minikube, and from another terminal, I have entered into the virtual machine that was started by Minikube, and I'm inside this. We were just looking at the images that were already present and containers that were present, and the container, the Hello World container that we created. Now let us look at any of these containers. Here we have listed the containers. Let's look at the first slide. There's a container ID. There's an image based on which the container is created, and the command, and it was been created, and it has name of the container. Let's take any one of them, right? So let me pick which one do I pick? Let me take this storage provision, or let's take the first one, the dashboard, right? I have copied this. So let me So let's here in our exercise, we say, let's look at any one of the containers and try to inspect by using the Docker inspect command and try to see what the networking specifications are. Let's do that right away. And I'm going to paste the container name here. And let me pipe it through more. Sorry, I typed PS instead of. Okay. So what you're seeing is some very interesting information about this container. At the top of it, you're seeing the ID that was created, that has been assigned to this container. It's a running container. That means when this container is constructed from the image repo, the ID was assigned to it, and it'll tell you what are all the options that were passed to the container runtime, and the current state of the program, the image based on which this container is built. And let's scroll down a little bit. We'll come back to many of these host configs in our later part of the lab. I will scroll down. At the end of it, you are seeing some of the network settings. So these network settings have been passed when the image has to be instantiated and the container had to be created. The container runtime makes note of all this, and it has stored them in its own internal structures. That these are the network settings for it. So you will see that it has not requested anything specific. This particular container has not requested anything. But if it had requested any of the ports, for example, if this was a web server, you will see this in the hands-on lab in the afternoon. You will see that this particular line, ports, would not have been empty. It would specify the ports that it has requested on the host system to be bridged to itself. So this is an example of how the settings that are specified uh, when the container image is built are propagated to the image manifest, and when it is pulled, it is passed out to the container runtime, and the container runtime keeps track of all the information, all the requirements that have to be met for this particular container when this image is instantiated as a container. Was everyone able to follow this? Were you able to do this on your Ubuntu system?
Yes.
Okay, great. Let's remember this important command called docker inspect. You will be able to learn a ton about what the information that is passed to a particular container when it was when a normal program was converted into a container form factor and uploaded when it is brought to the container runtime. These are the this is metadata that accompanies the container image. Now let's look at some of the storage challenges. We mentioned earlier that the basic nature of container is ephemeral. That means it comes and goes. It can be instantiated and it can be torn down when there are no more resources, or it can be restarted anywhere else. Now, some of the programs, for example, databases or web servers, they will have their own data. And while some of this data, if it is present in the cloud, then there is no problem, because no matter where the container is started, as long as there is internet connectivity, as we saw before, it can simply request access to the external network, and it can access the cloud storage as if it were on any other system. It wouldn't change anything. However, if the application is written such that many of the currently available applications depend on some local directories to have the data. That means they store the data in local directories, and whenever they go, wherever they go, they expect the data to be available. Now this is the first problem, which is can the container be started anywhere, and can we make the data available to the container wherever it goes? And how do we do that? And if the program, it must be persisted and stored. But that is the most basic of the problems. There are a bit more complicated challenges, such as making it distributed, like I just mentioned. Is it available anywhere the container runs? And we said that the container is extremely portable. For example, if I take the container and deploy it on a cloud, today I'm running it on my Ubuntu system. Can I run it on Amazon's cloud tomorrow? Now, how do we get the storage there? It provides a challenge. And let's say if you have multiple containers, I have a program that consists of two parts, and both of them, part A and part B, both need to access the same storage. How do we present the same storage to two containers? And what if they want to do it at the same time? This is a bit of a challenge because we said earlier that a container can run anywhere, which means one container runs in host 1, another one runs in host 2. How do we present the same storage to two separate containers on two separate hosts? This is a challenge. Consistency. It means we said that the basic nature is ephemeral, which means the container runtime or the administrator can shut down the program anytime and start it anywhere else. Now, what happens to the data that was in flight? How do we ensure consistency? And now another thing we said was this is extremely portable. You can take it from one place to another. Then natural thing that you have to worry is, okay, you are letting me take my data anywhere. How do I know that this data is secure? Now you're sending it to a lot of networks and other things. How do I know that my data is secure? There is some challenges there. And multi-tenancy. That means if you have, usually enterprises will have one large storage array that serves storage to many of the clients. Now, I think you saw that when in Suparna's presentation yesterday that some of the data centers have these huge storages with multiple nodes and terabytes and probably petabytes of storage. Now, uh, how do we do this multi-tenancy thing? Means you have in the container world, you have one tenant. That means all the containers should belong to a particular group will share the storage, but they won't share it with other tenants. How do we do that? There are some challenges in this, and there are all many technical solutions that are currently available, currently shipping products that provide this, and it is still an evolving field. So let's look at the basic thing about the persistent storage of a container. The basic nature of a container, as we said, is ephemeral. That means program that need to persist data. We are only talking about the case where it needs to be presented to the container wherever it runs as if it is in one of the local directories for the container. For example, you have a database and you have a program that's acquiring the data. It can move from one host to another. How do we present the data? If it is a cloud storage, as I mentioned, it is not a problem at all. It can be accessed from anywhere. So how do we deal with local storage? We deal with a special kind of a technique called a bind mount. What we do is we ensure that wherever the container is run, the host on which it is run is able to access the storage. First, the storage is acquired by the host operating system into one of its local directories, and then it is bind mounted. That means it is connected into the container's namespace into one of the directories. And when the container is evicted or moved to another place, we tear down this association and repeat the whole process when the container restarts again. The diagram that you see on the right side illustrates this. It means you have the familiar image repository, you have the developer pushing in the image, and the operations pulling in the image, feeding it to the container runtime, which instantiates the containers. But this container says, I want some storage. And that storage must now be acquired by the host system first. In this case, the big gray box that you see is the host, or the big white box, white waterline that you see is the host. It has to first acquire the storage, and for the container A, it is requesting a particular storage. That storage must be first acquired by the host, and it is placed in dir1, and eventually it is presented to container A only. This dir1 cannot be seen by container B or anybody else. And similarly for container B, when the storage that it has requested is acquired by the host and placed in one of the local directories under /mnt as dir6 and bind mounted into the container. But what the container sees is not what the host sees. The container simply sees that, I see my data under this place, and it goes on to access the data. And this process repeats every time it goes, every time it is deployed. Was that clear? And just want to pause a little bit here to see if there are any questions. All right. So probably when we inspect the containers and their persistent storage, you will be able to see that live on the Ubuntu system. So let's look at our system again and try and see. Let's inspect the container and see what. So let's do the same thing again that we did. Let's look at this particular container, and we are seeing the familiar container ID, and it says now. Let's look at the part that I'm currently looking at called host config. I have highlighted that in the Ubuntu terminal. I hope the fonts are not too small and they're visible. Please let me know. I can bump up the font size. Is that are the fonts visible clearly on your screens? I hope, yeah. If it's very hard to see, please let me know. I'll be happy to bump up the font size. So there's a particular configuration. That means when this container has to be deployed, the image says it needs the following bytes. That means it says the source and this. Take a look at this. It says this is what you see on the host system, and the container must be able to see it as etc hosts. So this is a typical example of a bind mount. That is, whatever is seen on the host, the container runtime takes this directory and it bind mounts into the container namespace as etc host. So the container, when it sees etc hosts, it is actually looking at the associated host on the associated etc hosts file on the OS at this particular path. It's a very interesting one. This is exactly how it's bind mounted. And there's a very interesting thing to note here. That means we talked about how the container is pulled, or how the image is pulled from the image repo and reconstructed by container runtime, and a directory is created for the container where it runs. So the graph driver section that you see describes where the container actually lives on the host and what is the directory that the container actually sees. Here you see there are four. One is there's something called a lower dir, there's a merge dir, upper dir, and a work dir. So essentially what's happening here is it takes the container image, the image is decoded, deconstructed into a directory, but any changes the container makes will not be carried over. It will be kept specific to that container so that the image itself, which contains the original directory, is untouched. The way it does it is using a type of a file system called overlay, where the directory that has been specified in the image is kept in the lower directory, and any changes the instantiated container makes goes to the first, it arrives in the merge directory, and then it goes to the upper directory. It never reaches the lower directory, which is actually where the image resides. So this way, the same image, the same lower directory can be used for different instances of the container. So this is a good example of how it uses special techniques. and the directory structure on the host to provide storage to the containers, which still see it as their own space, but they are not actually modifying anything in the original container image. Okay, so in this,
So this was an example of ephemeral storage, right? The graph driver thing was ephemeral storage.
That is correct. That is correct. This is the ephemeral storage, which means once the container is removed, once the container stops, all the changes that have been done goes away. Whereas in the persistent storage, that means whatever you see in the mount section that you're seeing in this terminal window, these are permanent. That means they are bind mounted into the container namespace from the host, and they remain as long as the host has the same. That means wherever it acquires from, if it is from a constant source, wherever the container goes, the same storage is presented anywhere. The container runtime does not make any changes, or it does not manage this space. It simply bind mounts it, lets the container do changes, and when it runs back again, it restores them to where they have to be. So I'll pause for a minute here to see if you have had a chance to try it and if you have any questions. All right, we'll move on. And if you have any questions or anything, please feel free to raise hand or type it into the chat room. Earlier, I was not looking at the chat room, but I will ensure that I will look at it and try and answer any questions. So switching gears a little bit, I want to talk about the orchestrator. We just mentioned, many programs can be started in a single OS instance, and we saw how in a typical setup, you will have a lot of bare metal servers, and you'll have hypervisors installed on it. There'll be hundreds, probably thousands of virtual machines. And if each of these virtual machines start running so many containers are capable of running them quickly, the way you package the container and the way you deploy it makes it so easy to move them around. It becomes very hard to uh, have a single place of control. How do we know which container is running where? I mean, I have, let us say I have 100 virtual machines, and I want to move the container around to do its job anywhere. I can start and stop the container anywhere I want using the commands that we just saw. It becomes quite unmanageable as the number of containers increases. So there is some kind of a uh, automated workflow, or there is some extra additional software that is needed that can orchestrate all these things. Because when we get a container, we first have to see, okay, this particular program says it needs so much of memory and it needs so much of CPUs, and first I have to find a particular host that can meet these requirements, that has so much of free space still available. First I have to hunt for it, then start it, and if something happens there, I should constantly monitor that container, and for some reason if it crashes, I should be able to restart it on another host which has similar requirements. All this is too complicated to be done manually. So that is why we have, there is a new layer in the container world called the orchestrator. The container is typically one stateless program that performs a small function, but it is part of a larger program, which can be connections of many such programs. So managing the large number of containers by hand manually is impractical. So to do all this system is the orchestrator. So in the beginning part of the orchestrators, many orchestrators came into the market, and typically Docker Swarm and Mesos and Kubernetes. But because of the quick adoption and the facilities provided based on many factors, today the most common name that you hear is Kubernetes, and Kubernetes is the most widely used orchestrator. And for all practical purposes, when someone says orchestrator, it has come to mean Kubernetes these days. So although orchestrator is a very generic term, and Kubernetes is one implementation of the orchestrator, the generally orchestrators come to mean Kubernetes, and you will see that they are used as interchangeable terms. But remember, it's helpful to remember the differentiation. And Kubernetes is open source, and it was the first one to graduate from Cloud Native Compute Foundation. And for those of you interested, you can just visit cncf.io. You will see how many programs are currently in the sandbox and how many of them have graduated. The first one to graduate was Kubernetes, and it has a set of requirements about what it means to graduate. It is quite an interesting read. It has started in the last few years, so it will be very useful for you to know what's going on in that world. So Kubernetes is the default orchestrator that you will see in many systems, and many commercial versions of Kubernetes are available, even in the cloud platforms. And Amazon AWS offers its own version of Kubernetes. Google on their cloud platform offers its own version of Kubernetes. Red Hat ships its own version of Kubernetes, and so on. There are many such commercially available platforms, but for most of the purposes, they all contain the same version of Kubernetes that comes from the open source. Now, you may want to draw a parallel to this of how the Linux world works, whether it is CentOS or whether it is Ubuntu or whether it is SUSE. Any of these distros of Linux you use, the version of kernel they use, they all come from the same kernel source. They all share the same Linux kernel, and although they may have different versions, they all come from a single source. And you can draw a parallel to this of how the commercial versions of Kubernetes distributions that are available are tied to the open source Kubernetes that is available. And one of the things that I want to emphasize here again, I have said this before, none of these programs, it has been because of the way the Linux kernel has been built, as Suparna mentioned yesterday, you saw many of ideas were ahead of their time, but they have come to use now, including Kubernetes or Docker. None of them have required any changes to Linux kernel. It has been built on top. They are completely in user space. And here is the picture with enhanced version of what value that Kubernetes means. You see all the familiar blocks that you saw earlier. You have this dev tools that push the image, then the ops tools that pull the image and deploy it on the container runtime, which explodes it into the local storage and instantiates the containers. And the local host acquires the external storage, required storage, and then attaches it to the containers. We saw all this familiar. Now we have an extra module that has come in called Kubelet. So Kubelet is the program that is installed by Kubernetes on every node that has to be part of a Kubernetes cluster. And this Kubelet is the one that takes care of automating all the work that you are doing in ops and from the operations part, that is uh, acquiring the image from the image repo, looking at the requirements and scheduling it on the container runtime, and when the work is done, removing it and then reporting it. And the kubelet is controlled by a master node. The Kubernetes master node that will have all the necessary logic to figure out whether this program should be run on this node or not. So the Kubernetes program running on the master node decides which node should run it based on the information that it obtains from kubelet, and kubelet takes care of actually deploying it on that particular host. So you can see that the Kubernetes has the capability to orchestrate where the container should run, and it orchestrates it via an agent on running on a particular host, and the name of that agent is kubelet. We will see in the lab today by scheduling the program, and we'll see how many nodes are a particular Kubernetes one is controlling and how it deploys in various stages. I will pause for a minute here to see if there are any questions. All right, let's move to the So one of the fundamental notions in Kubernetes is declarative and not imperative, which means whenever you specify, so in the Kubernetes world, instead of using the ops tools, that means we saw that how the kubelet takes care of, takes over the functionality of the ops tools. That means you do not have to run any of the Docker commands to pull the image and then deploy it, even though the image contains all the information. In Kubernetes world, what you do is you create a manifest. You tell Kubernetes, this is how I want my program to run, and you leave the specifics of how that requirement is met by Kubernetes. For example, you can say, I want 2 instances of my program running, and you do not go and give step-by-step instructions on, okay, run it on one node, run it on the other node, and if one of them fails, restart it on this node or that node. You do not do all these step-by-step instructions, but you simply say what needs to be done, and you leave the details of how it is achieved to the system. That is the difference between declarative and imperative. So every time you specify, for example, when you want to deploy an application, Kubernetes tracks that request using an object. And there are 2 sections in every object. One is called the specification, short as spec, and the other one is the status. So this says what is the desired state of this object, and the status says what is the current state of this object. And Kubernetes constantly tries to match the spec with the status to bring it to that level. And it does not mean it's always successful, but it keeps trying because it is dependent on many factors. For example, if you ask if the specification says I want 100 instances to be run, but there is not enough memory or not enough nodes to meet that requirement, it doesn't mean it will not be done, but it will keep trying. It may not be done, but it will keep trying. And this API model scales to a large number of participants. And for those of you who are familiar with distributed computing, you will know that in many traditional models, there's a master node who tries to control every node by polling them, by telling them what to do, and constantly communicating with them and trying to get the status. So Kubernetes has a decentralized model, has sort of a broken into 2 parts, which is it simply updates the API objects about what state is necessary, and it leaves the individual nodes to uh, poll the object and try to do what is necessary to bring it to the state and update the status back. So this way, the master node will not have to communicate to 1,000 nodes. It simply registers the nodes and it sends out a notification that I want this to be done, and let the nodes, each of the participants, do their work in moving the object towards the required goal. So this way it can scale to arbitrary number of clients. So all this is done by using one of the central concept of Kubernetes called a resources. That means a resource specifies, for example, a pod. A pod is essentially a collection of programs that are scheduled together, form a part of one program is typically maps to one pod, and it is a resource that is defined. So Kubernetes knows how to handle this resource. And when you say that I want to instantiate a pod, an object is created whose end state is declared, and Kubernetes tries to meet that. So an object is an instantiation, and resource is what Kubernetes knows about handling that type of an object. And one of the key things in Kubernetes is a distributed key value pair, where all the objects, all the resources are kept and tracked, which is the status of the object and how many objects are there, and what are the specifications. And anytime a end user wants a change in it, it is updated in the distributed key value system, and the rest of the participants will refer to that. So everything revolves centrally around the database that it stores. All the APIs, everything is served by the single distributed key value pair, which is made highly available by running it on multiple instances. So let's do a quick exercise on to get some hang of what Kubernetes is about. So let me open up the Ubuntu window again. Until now, we have been doing only the Docker part of it. That means we were doing on the container runtime. Now let's do it. And here is my, you will see that this is the system inside which I am running it. But since I'm running Kubernetes now, I do not have to be inside the container host. I can be outside of it. This is where I have run, I have initiated the Kubernetes cluster using Minikube. There, I got some information. Let me say, you can see that there is one node running which we started, and this is what it shows as the number of nodes available in the system. Let's see how many pods are currently running. Wow, there's absolutely no programs that have been scheduled to run because we haven't started any program. But there are some system pods. Kubernetes itself has started some of the some programs to run. So let's take a look at what pods are currently running, including all the namespaces. Here you will see that many of the pods, each of these pods probably refer to one or more containers. And when we saw inside this system, we saw that so many containers are running. So more than 20 containers are running, but you will see that it's actually running lesser number of pods here, which goes to show you that one pod can have multiple containers running. And each one of these are easier. That means we have specified, we can describe any one of these pods. Okay, there's something I need to figure out. In any of these systems, we can use, just like we use Docker inspect, we can use, probably I'm not using the command correctly. We'll come back to that during the lab. The point here is, just like we inspected the Docker, now we are going to do it at a higher level. We are going to be sitting outside of the system where the containers are actually running from a management console, and we are looking at all the programs that have been scheduled. Suppose that if there were 5 nodes, and there were 500 pods running with 10 containers each. There will be actually 5,000 containers running, but I do not have to monitor 5,000 containers. I will just have to look at the 500 pods that I have scheduled, and I can do it all with from the command line from a management station using kubectl command, and it can even be visualized graphically with a Kubernetes dashboard. We'll see about the Kubernetes dashboard in the lab. So I'll pause for a minute here to see if there are any questions or if you have any doubts or you didn't follow anything. All right, I just want to just guess a little bit and talk about a special type of a storage called for how do we exactly attach an external storage to a Kubernetes pod. So usually when a container program is run, usually they have their own preferences of where they want their storage to come from. So a private cloud, from an enterprise array. So Kubernetes has defined a special type of an interface called container storage interface, and anyone who wants to attach their storage to the containers running in a Kubernetes system can write a driver and make it part of the Kubernetes system. So that way, when a container is launched, the storage from that array or from that external source can be attached to the container. The pattern follows very similar to how we attach the persistent storage. You see the familiar picture here. So in this particular case, I'm showing the box where you have the image repo, you have the dev tools, op tools. Kubelet can download the image and it can schedule it on the container runtime and on the local storage. directory is constructed and the containers are instantiated. We have a container array that is instantiated that is requesting a storage from an external storage array. In this case, it is outside of the system. So the Kubernetes deploys another pod called the CSI driver that knows how to talk to this external storage. And it is the responsibility of the CSI driver to acquire the storage onto the host and then present it to the container. So this is, you can say that this is one level of sophistication above the bind mount that we saw earlier, where you had to do it by hand. You had to first get the, first acquire the storage onto the local host first, and then present it to the container. Here, you can let the CSI driver itself do the job. So you can see that more and more things have been eliminated from having to be done manually, and everything is done through programmatically and through the API controls. Here, what I mean is the storage that is necessary is specified by the application. Kubernetes identifies it and it instructs the kubelet to get the program necessary to bring the storage in first, and the storage is brought in first, then the container that requires the storage is then launched. So everything is done and orchestrated by the container. And now you can see why the orchestrator gets its name as orchestrator. So what the next thing that Kubernetes and this new model has enabled is what is called as the microservices. So it is a paradigm shift in application architecture. Earlier, you used to see large programs that were monolithic programs. It had huge number of accessory programs. Everything possibly started as a single program or a bunch of programs, and they were running all the time. So you had some programs running as daemons and some programs running as libraries and some programs running as network services. So many of these programs ran together in perfect synchronization to make a larger program. So from this model, what the container allows you to do is microservices. That means we said that the basic nature of container is ephemeral. So probably we can split off some of these functions. Many of the functions, many of the helper programs can be invoked only when necessary. So that way they do not keep running on the system and keep consuming system resources, even when they are not being actively needed by the main program. So when the main program needs it, it simply can request that the program be started, and the program starts up, does its job, feeds the main program what it wants, and it disappears. And it is invoked again when necessary. So this is called what is called as a microservice. That means you can think of it as a function call, but that is instantiated only when necessary. A remote function call backed by a remote program that is instantiated only when necessary. And the infrastructure today exists so that the function can execute anywhere. It does not even necessarily have to execute on the same host where the main program is running. In fact, all of these can be spread out in many places, even though the program itself can specify that I want to run it in one single place. So one of the things that it enables is application upgrades. For example, in a traditional model, if you have a monolithic application and if you wanted to get a new version of the application, you have to take down the whole application and bring the new application and restart it all over again. In the microservices model, if there was one change in one part of the program that is implemented as a microservice, you can only change that particular program, and you can deploy a new version of that program only and you do not have to take down the main program at all. The main program keeps running. That way the availability remains, but only this program is switched. Only the corresponding program that where an enhancement or a bug fix was done, only that was upgraded. So this kind of gives a new meaning to how the application availability can be kept up, and the faults in the program are reduced to even smaller fault domains. So if there's a problem in one service, it does not affect the rest of the services, and only that can be patched. So this is one of the advantages of monolithic versus microservices. And although the idea of a microservices has been around, now we have the full-fledged Kubernetes platform that enables this to be deployed and realized in a much more elegant and very easily. So that brings the end to what I wanted to share in terms of Kubernetes and containers. So I want to pause here a little bit to see if you have any questions or if you had any other comments. I'd be happy to answer any of your questions.
Hi, I have one question. So, what's the difference between microservice and serverless?
In terms of technology, they are more or less the same, which is in serverless, what it means is when in the serverless, you write a program and you do not specify you do not care where it's run, and you do not care how it's run. All you care is this program must be run, and this is the way I will collect the results, right? And you hand it off to a service that runs it, finds the most suitable candidate where the program can be run, and it acquires it. And microservice in terms of implementation is the same. That is, it's also packaged as in one form to be run independently, and it is scheduled independently and on demand by the main program or whoever is invoking it. They are scheduled, and the result is provided, whichever form is agreed on between the service producer and the service consumer. So typically in serverless computing, when you say it may be a large program, I mean, for example, you have written a program that takes in a text file with a large matrix, and it inverts the matrix and sends you back the data. So you don't care where it's run as long as the matrix is inverted. In case of a microservice, you can think of it as it is doing one part of the work of the main program, and it runs in the same way. It has a specified service interface that is only visible to its main program, invoked on demand, and it is unloaded when it is no longer necessary. So in terms of technology that enables, they are the same, but the way they are consumed in the real world may be different. Serverless program is a standalone program on its own. Microservice is probably something that is subservient to a main program. Did that answer your question?
Yeah. Thank you.
Sure.
There's one more.
Yeah, one more thing. I mean, the realization of serverless might happen by having containers under the covers. So what you might have is that you have, because starting up the containers and is an overhead, right? So you might actually have, when you're running a functionless, function as a service, right, which is one instance of serverless. So it might spin up a container and then keep those containers cached, and then use that to instantiate that function within that container. So there are, those are different realizations of that, concept of serverless that could be applied, and there might be frameworks which will try to do that.
Thank you, Suparna. I think that's probably should clarify that, and hopefully that was useful. Any other questions? Any other comments?
Yeah, that's really great. So I do. Sorry to interrupt, Mohan. Please go ahead.
Mohan, were you about to say something? Oh, Mohan went on mute. So Adi, go ahead.
Yes. So, I mean, obviously this is great, and this has been really taking off in the past 5 to 6 years, containers, microservices. But I'm not exactly clear on what's the benefit between a a monolithic architecture, or as we like to call it, SOA, service-oriented architecture with these monolithic centralized buses, versus our microservice. Except for I mean, it's very hard to say that these are easier to upgrade or troubleshoot or patch. That's not a reason for a customer to move from an on-premise, so a monolithic architecture to a microservice. I'm still not convinced to buy this architecture. That's what I'm asking you for the technical detail, like what truly makes microservice better than SOA.
Okay, so probably I think there were two parts of it. You said why would a customer move from one technology to another, and the reasons for a customer to move from one place to another is definitely not because something is a cooler technology, but something that gets them done their business faster. And whether it is they're running it on-premise or whether they're doing it on the cloud, it doesn't matter. So what they'll do is, can this make my life easier? Can I get the same thing done with lesser resources? Can I get the same level of service from different resources? And one of the things that matters to the customer is how much downtime um, does this provide? And many of the vendors today, they provide their applications in the container form factor, and they say, instead of running it the way you were running as a monolithic application, we can provide it in a container form factor, which ensures that you can we have isolated many of the services into microservices. So that way our response time will be much faster, and you will not have downtime of the whole application as opposed to having uh, as opposed to having only one part of the service back. So this is a value proposition for the customer. That is, it helps them maintain higher levels of service, and it helps them have the same experience as far as their customers or their applications or their own usage is concerned. They will see no difference except that they will have a better maintainability, because many of the customers, for them, acquiring of the service and maintaining them are two separate costs, and maintenance is what or the is kind of the more cost you reduce in terms of how much it costs to actually run this their application, the value comes from there. So while not every situation says it is not a one solution fits all. So I cannot say if you move to microservices, it'll automatically save so much. But there are situations where the monolithic itself is cannot be broken up anymore than what it is. So they'll continue to run that, and where there is where it's feasible, the microservices make sense and it reduces their cost of operations or reduces their downtime significantly. So there is no universal solution that works for everyone. But this architecture is the one that enables microservices to solve some of the problems in areas where it can be solved.
Yeah. Okay.
So yeah, I think the main benefit, I think, like Raman was saying, is for the vendors who are providing the service, right? So it's for the platform as a service vendors. I think it makes it simpler for them. From a customer viewpoint, I think they still get the same experience as what they would have in the older architecture, and they can get it now on a cloud kind of system without even knowing what's really happening there. And then, like Raman said, I think it simplifies things for the developers, I think, in terms of troubleshooting, patching, etc., and application upgrades. So it's more of the developer scenario which it helps, rather than a customer who probably gets the same experience and maybe a slightly better one also.
Thank you, Mohan. I think that's very well put.